Hello, everyone. My name is Ray Li. I'm a big data infrastructure engineer from Bilibili, which is a leading video sharing platform in China. And today I'm glad to share with you how we use Apache Iceberg for lab scenarios. First, I'll talk about the background of our project. The next two sections will focus on query optimizations, as well as a table management service called Magnus. And finally, I'll talk about how we are doing right now. Okay, let's get started. The project was launched in 2021. At that time, our data warehouse was built around Apache Hive. And one problem with Hive is that query performance is not very good. So if users want to run interactive queries, they often need ETL jobs to copy Hive tables to other systems like ClickHouse. And of course, such ETL jobs increase both maintenance cost and data redundancy. So our project aims to solve this problem. Our goal is to introduce a new table format which has good query performance and so can be used for OLAP scenarios. And it should also be an open data format that can be accessed by different engines so that we don't risk increasing data redundancy by using it. And we also want it to be easy to use. We don't want to disrupt current user behaviors or require users to learn a lot of new stuff in order to use it. So with this in mind, we chose Apache Iceberg as our new format. Why? The most important reason is that Iceberg has a well-designed format specification regarding how data and metadata files are organized. And this makes it very easy for us to extend to implement the features we need. And secondly, it's a very smooth transition moving from Hive to Iceberg. All the engines we use to process Hive tables can also process Iceberg tables. So our users can continue use the existing tools with the new format. And sometimes they don't even need to be aware of the underlying change. And of course, there are other benefits such as transaction isolations and the ability to update and so on. And this is the architecture of our data lakehouse built around Iceberg. On the left side, you can see we support data ingestion into Iceberg in both batch and streaming manners. Iceberg tables are stored on HDFS, and we use Alexu to accelerate access to the underlying files. At the moment, we only cache metadata files with Alexu because metadata files are usually smaller and may be scanned multiple times in a query. We choose Trino as our engine for interactive queries, and we implemented a table management service called Magnus. Then on the right side, we support exporting Iceberg tables to other systems if that's needed. Okay, now let's look at the query optimizations we've done. A typical analytic query usually contains filters to select relevant data from a table. So the first idea came to mind is that if we can skip scanning data files that don't meet the filter criteria, then it will considerably improve query performance. How to do that? Iceberg stores various statistics for each data file. And among these stats, we have the lower and upper bounds of each column. So if a filter condition is out of the range determined by these bounds, then it's safe to skip the file. But to make sure we have a good chance to skip the file, we need to sort the data by the filter columns so that each data contains only a small portion of the total value domain. And we call these columns distribution or ordering columns, as they determine how data is distributed among the files. In this picture shows 3 queries from our benchmark tool, each filtering on a different column. So to optimize these queries, we need to sort the data by the 3 columns. However, an ordinary sort doesn't work here. By ordinary sort, I mean to compare the columns one by one. That is most likely to only work for the column, and demonstrated by our test result here. So to introduce the order and distribution.
Hey Ray, your audio is a little bit off. Would you possibly be able to go ahead and move a little bit closer if you can to your router?
Is this better now?
This is better. Yes, perfect.
Okay. Sorry. Okay. So to solve the problem, we introduced the Z-order and the Hilbert curve distributions. Both of them can do multi-dimensional ordering. So using the same test cases above, we can now skip data files for all the 3 queries. And our benchmark shows that Hilbert curve has a slightly better cluster effect. So that's what we choose to use in production. But we also have some limitations here. First of all, the number of ordering columns is limited. So in general, the more columns we use, the less cluster effect we can expect for each single column. So in production, we allow at most 4 columns. And another limitation is false positive, because a value being within the boundaries doesn't really guarantee that it exists in the file. So we also implemented data skipping indexes. An index is usually defined on a column, but we also support index on an expression. For example, we can define an index on a nested field in a JSON column. And each table can have multiple indexes, and the definitions are stored in the metadata file. And for a data file in the table, one index file is generated for each definition. And the metadata of the index files is associated with the data file in the manifest. So at query times, these index files will be used to determine whether the data file satisfies the search condition. Most index files are also standalone files on HDFS, but if an index file is extremely small, then its content will be embedded in the manifest. Okay. Index files can be generated when a data file is written into the table, or they can be generated by asynchronous Spark jobs. This picture shows how we track index files. And in this example, we have defined indexes on 2 columns, SCT and CCT. So each data file will have 2 associated index files. And in this case, both index files are standalone files. So we store the passes to them in the manifest. We implemented several different indexes. The simplest one is Bloom filter, which is small, with a controllable false positive probability, but it can only be used for point queries. We also have bitmap index, where we store the row numbers for each value as bitmaps. It's usually much bigger. but it doesn't have false positive, and it can be used in both point and range queries. And in addition, we can also do intersections on the bitmaps for conjunctive filter conditions. Let's say we are looking for data where column A equals 1 and column B equals 2. It's possible that there are records satisfying each condition alone, but there is no record satisfying both of them. Now, Bloom filter index cannot detect such a case, but a bitmap index will do. We also have another index type called Bloom RF. It's similar to a Bloom filter, but it can be used in range queries. So now that we have index files in place, we need to make Trino to use them. When Trino scans an Iceberg table, the coordinator is responsible for generating splits. Each split is a segment of a data file and will be distributed to a worker node for reading and processing. The coordinator calls the plan files API in Iceberg to generate splits. The API reads the manifests to retrieve the required data files. The embedded index files are used here to filter out manifest entries that don't meet the search conditions. And for standalone index files, their metadata will be sent to the worker nodes as part of the split. And on the worker node, we will use this metadata to read the index file and check if the data file satisfies the condition. And if it doesn't, we will create an empty page source to indicate the split can be skipped. Okay, that's it for the data skipping features. Now let's look at the optimizations for aggregations. An aggregation typically reads a lot of input data and outputs aggregated results, which are much smaller in size. So the idea is to pre-compute and materialize these results and use them for the query. So that will save us a lot of I/O and CPU costs. We call this feature aggregation index, or AGG index for short. An aggregation index is defined on a table. It can involve a single table, or it can involve a star schema model. And if it's a star schema model, the aggregation index should be defined on the fact table. Each aggregation index essentially defines two things: dimension columns and aggregation functions. A table can have multiple aggregation indexes, and the definitions are also stored in the metadata JSON file. And also similar to data skipping indexes, for a data file in a table, an aggregation index file is computed for each definition, and the metadata of them is also associated with the data file in the manifest. And since aggregation is computed at the file level, we need to store the mergeable states of the aggregation functions, so that a query can merge data from multiple files to get the final results, right? So for example, we store the sum and count values for the average function, and we store a bitmap for count distinct. Let's look at an example. This is a test query from star schema benchmark. And in this query, we join the fact table line order with 3-dimension tables and compute the yearly revenue for a certain brand. We extended Spark SQL so that we can write a statement like this to define the aggregation index. Now, notice that the columns from the group by and filter clauses should be defined as dimension columns. Therefore, we have D year, P brand, and S region as dimensions. Now you may wonder why why this statement works, because the 3-dimension columns are not from the fact table, right? Well, we implemented a feature called correlated columns, which are some kind of virtual column that can be derived by joining with other tables. So for this statement to work, we have to firstly add the 3 columns as correlated columns to the fact table. And aggregation index files are generated by asynchronous Spark jobs. And for the above example we just talked about, the right side of the picture shows the logical plan of the Spark job to generate the aggregation index files. And again, it knows how to join the dimension tables because the information is carried by the correlated columns. And since aggregation is computed at file level, we will add the data file path before all the dimension columns when doing the group by, so that we don't aggregate records from different files. And then we shuffle by the file path so that each writer sees all the data for a single file. And they can use this file path to determine the boundaries between each file and write the aggregation index files out as ordinary ORC or Parquet files. And after that, we will rewrite the manifests to associate the aggregation index files with the data files from which they are computed. And work is also needed on Trino side to use aggregation index. We implemented an optimization rule for this. The rule, when the rule finds an aggregation node, it checks the plan to see if it matches any aggregation index. And certain conditions are checked here. For example, join types should be the same, and aggregation functions and dimension columns in the query should be subsets of those defined in the aggregation index. And if everything looks good, the original logical plan on the left side will be replaced with the one on the right. And in the new plan, the table scan node will be marked as AGG index mode, which means for each data file, it will read the associated aggregation index files rather than the data file itself. But here is a problem. Remember that I said aggregation index files are generated synchronously. So what happens if only some of the data files have aggregation index files with them? This can be very common if the data is written by a streaming job, right? The answer is for data files without aggregation index files, we compute them on site and then union with the existing aggregation index files. So the new plan will actually look like this. We separate data files in the fact table into 2 sets based on whether aggregation index files exist or not. And the left side of the union processes those files without aggregation index files. It's basically the same as the original plan, except that the aggregation node is replaced to compute the aggregation index. And then it's unioned with the right side and fed to a final aggregation node to merge the results. Okay, we tested the optimizations with star schema benchmark. The data size is 1 terabyte, and the queries are run on a 5-node Trino cluster. And you can see there is great performance improvement in the chart here. Okay, now let's look at the table management service, Magnus. Magnus has 3 major responsibilities. The first and most important one is to optimize Iceberg tables. Whenever new data files are added to an Iceberg table, Magnus schedules Spark jobs to optimize the data. And an optimized job can redistribute data, generate index or aggregation index files according to the table configurations. So all the optimization features we just talked about rely on Magnus to really take effect. And secondly, Magnus provides a web UI for us to inspect table internals, such as the commit history or the data sizes for each partition. It also displays the optimization status. For example, how many files in the table have index files with them. So this can be very useful to debug slow queries. And lastly, Magnus analyzes user query history in order to improve table configurations. For example, if a column has been frequently used in filters, then Magnus can add it to the distribution columns or define an index for it. Okay, let's go a little deeper into the details. We added a commit listener in Iceberg. So in our production, whenever a Spark or Flink job commits new data files to an Iceberg table, a notification is sent to Magnus so that Magnus can schedule optimization jobs accordingly. And each optimization job handles a bunch of snapshots. We set thresholds on both data size and the file count to trigger the jobs. And we have 3 levels of jobs. If the snapshots produce enough number of files, but doesn't reach the threshold of data size, then it means we have a lot of small files, right? And in that case, a level 0 job is triggered to merge these files. And when the data size threshold is reached, a level 1 job is triggered to do the actual optimizations. Most of the time, we can stop with level 1 jobs because the output has all the optimizations we need and can be used to accelerate queries. But sometimes we will need another level 2 job. Level 2 job can only be triggered by outputs from level 1 jobs, and is only needed if a distribution is defined. And the reason behind this is we may get better cluster effect if we distribute with more data. And to improve table configurations, we make Trino extract patterns from each user query. For example, we want to know how it filters data or what aggregations it computes. And the query history is also stored as an Iceberg table. And every day, Magnus analyzes queries from the last week to decide if there are better configurations for the table. Okay, now it's the last part. So how are we doing right now? Currently, our Iceberg tables are mostly used for BI reports or compute BI metrics. It's suitable if data is written once and queried many times. We have over 2,000 Iceberg tables, and we have 2 Trino clusters with a total 108 physical nodes. And we serve about 3.5 million queries each day. The 95th percentile response time is within 3 seconds. And on average, distribution and the index help us skip over 80% data files in a query. We are also exploring some new use cases. for example, we are trying to use Iceberg and Trino to do some log analysis, and implemented some features for it. For example, a typical query on log data will look for some certain text in the log messages, and text searching is very CPU intensive. So we implemented token indexes, which are similar to inverted indexes, and can tell us which rows contain the text of interest. And another optimization is for top-N operations, because most of the time, a user is only interested in the earliest or the latest bunch of logs in a certain time range. So if we sort the logs by time step in each data file, then we can improve top-N performance in Trino. We also have plans to make Iceberg as our default format and migrate existing Hive tables to Iceberg. But to do that, we also have some problems to solve. The first problem is when a user wants to list partitions in an Iceberg table, it's computed by reading all the manifest files. So it can be much slower compared to Hive if the table has a lot of files. And another problem is commit throughput. So each commit to an Iceberg table needs to acquire a table level log in the Hive meta store. That is to maintain the transaction isolation. And this log can be a bottleneck if there are many jobs writing to an Iceberg table at the same time. Okay, but good news is the Iceberg community already has solutions for these two problems, and we are in the process to integrate them into our production. So hopefully we will see more adoption of Iceberg tables in our production very soon. Okay, that's all for my presentation, and thank you very much for your time. Thank you. Hi, I'm Pevin.
Yeah, so nobody heard anything. Okay. So once again, thanks, Ray. And now we'll be doing questions. So please go ahead and drop your questions in the Q&A tab on the top right. And then if you do want to come on camera as well to go and ask a question, you may do so. I know there's been a few people that have requested to come on camera since the beginning of the presentation. Just know it's for Q&A only. All right, so the first question here, right? Any reasons for not using Alexia for data and just for metadata? Ray, did you hear my question?
Oh, sorry, I missed the question.
Okay, let me repeat the question. Any reasons for not using Alexio for data and just for metadata?
Oh, we are also exploring options to cache the actual data files if they are repeatedly scanned by different queries. But in the beginning, we just cache metadata files because that's most likely to fit into the cache in Axo. Yeah.
Okay, perfect. Next question here. Let me scroll down. Okay, are you using Iceberg with Trino for queries to show data on dashboards and UI? That's the first part. The second part of the question is, how do you manage query latency for large volume data?
Yes, we do use Trino and Iceberg to for example, for the business intelligence dashboards, and I don't quite get the second question. Can you repeat it for me, Pavan? Sorry.
Yeah, the question is, how do you manage query latency for large volume data?
Mm-hmm. So most of our use cases focus on the datascaping. So, for example, it's possible that the table has a large volume of data, but to compute the dashboard, maybe only a small portion is needed. And so our optimization is to make sure we only scan the relevant data files and skip those that don't meet the search condition as much as possible. But of course, if the query semantically needs all the data in the table, then it probably will take much longer time.
Okay. All right. Next question. The index file mechanism, is that part of OSS Iceberg or your custom implementation?
That's our customer implementation.
Okay. Do you plan to contribute indexing and Hilbert curve to Iceberg project?
I think the OSS Iceberg already has the order and the Hilbert curve, if I remember correctly. When we implemented the feature, it didn't, but I think now it already has a Hilbert curve distribution. For indexes, we currently don't have plan to contribute to the open source, mainly because we don't have the bandwidth to do that. But I think we are open to that option, and maybe we can do that sometimes in the future.
Okay. All right. The next one is a two-part question, Ray. Can you expand the level 0, 1, and 2 job internals? Are you calling Iceberg built-in task or merging files through a custom logic or code?
The level 0 job only merges small files. We implemented the logic. It basically just read the small files and write the records out to a single larger file. So I think there's nothing special with the level 0 job. For level 1 jobs, we need to do the distribution, and we implemented the order and the Hilbert curve distribution as a customized shuffle partitioners in Spark. So I think the logic is mainly implemented in Spark, and we use that shuffle partitioner, and then it will distribute by the multiple filter columns. Okay. I'm not sure if that answers the question.
Well, the anonymous person that did ask that question, if you want to ask an updated question to that, please drop it in. Next question is, where can I find more information about Magnus?
Magnus.
Yeah.
More information about Magnus, right? Oh, okay. At the moment, I don't think there is more information about Magnus. It's a total internal project, and so I don't know. I'm glad to share share more details if you are interested. But I don't think we have plans to open source it or put the code somewhere. Maybe not. That's not the plan.
Okay. All right. I know we have a few people who want to come on camera to ask a question. So let me go ahead and do that now. So let me go ahead and bring on the first person here. Hi, Shahal. Can you hear us? Okay. Maybe not. Let me try the next person. Hi, Skander. Can you hear us? Okay. Maybe not. Let's just go ahead and go with the questions that we have that did come in here. Okay. So where was I? Okay. So the next question is a two-part question, right? Trino SLAs are generally in tens of seconds or minutes. That's the first question. The second part of the question is, how are you achieving 3's latency? Is it because of the index files with Bloom, Bitmap, or Bloomar indexes?
Mm-hmm. For us, the SRAs are about 10 seconds. Yeah, and most of the query optimizations. Most of the queries benefit from the data skipping features, like the distribution and the indexes. So I think for the second question is I think that's the answer for the second question. The distribution and the indexes helps us to get the 3-second response time. Yeah.
Okay, great. Next question is, what Iceberg version is Bilibili using internally? I think the newer shall solve the problem of Hive catalog commit throughput.
Mm-hmm. Yeah. Yes, we are currently using an relatively older version. It's 0.13, I think. Yeah. But we are in the process to upgrade to 1.4.3. Yeah. So, and we are also aware that the community already has the lock-free mechanism to commit data to Iceberg. So hopefully we will be using it very soon.
Okay. Next question is from someone saying, I am using Iceberg table in AWS Glue catalog. And how can we enable Agintex in Glue catalog?
Sorry, enable aggregation index, right?
Yeah.
AGG index.
Correct.
That's also an internal feature, and we haven't contributed it to the open source. So I guess that you cannot use it in AWS.
Okay. Next question is, what compression codec are you using, and did you find an optimal compression level?
Okay, I guess it's about the compression codec for the data files. So if that's the case, we are using the STD for compression, and our data files are stored as ORC files. We don't investigate too much about the compression codec. So that I think the STD has a very good compression ratio. So that's what we use.
Okay, perfect. I don't see any of the questions that have come in the Q&A tab or to come on camera. So with that, thank you guys all for joining us, and for you, Ray, for a great session.